should be able to hear me now. Can you hear me okay? No? How's that? Is that better? Luckily, I'm not going to say very much. Can you hear me okay? Yeah, you can hear me now. I can hear me now. So, fantastic. Well, it's great to see you all. So, thank you so much for coming along. It's a pleasure to have you here tonight. And also, we are live streaming. So, we have some people watching from the comfort of their own homes. And we hope that they're going to enjoy the evening too. We're here tonight to listen to the words of an exceptional Exonian, Professor Ed Hawkins, MBE. You'll know that Ed is a climate scientist, a professor at Reading University, and creator of the warming stripes, which are seen everywhere from BBC News to Reading FC's kit and his mum's scarf, which she's wearing right now. He was awarded the MBE in 2021 and received the Kavli Medal in 2018. And our geography department regularly refer to him as Geography and Climate Change Royalty, which is no lie. We're very privileged indeed to have him with us this evening. You might be interested to know that Ed actually started his academic life as a physicist, not a geographer, at Oxford, and completed his PhD in astrophysics at Nottingham. He then did a master's, deciding that he wanted to work for the Met Office, but never managed to get there, staying instead in academia. He's been at Reading at the National Centre for Climate Science for nearly 20 years. Ed really is an exceptional Exonian. Not only did he and his two brothers attend the school, but also his father, Tim, who was also a governor and is sitting on the front row here, and his mum, who also worked on the staff team. We're very grateful that he's here today to bring his expertise to inspire us all and hopefully make us think a little bit too. Before I hand over to Ed, I've got two housekeeping notices. First of all, please no photography this evening. Ed has kindly agreed that we can record the lecture and we'll make sure that's available to you afterwards. And also, we have no scheduled fire alarms. So if the fire alarm does go off, then please evacuate using the fire escapes to my left or my right, and one of the team will help you if that is the case. But as I say, that's not intended to happen. So if it does, it's real, and we need to do something about it. So now I'm going to welcome Ed, who's going to explore for us tonight climate change, our past, present, and future. Over to you. Thank you very much.
So thank you very much for the invitation to come. It's fantastic to be back here after so long. The school's changed an awful lot since I was last back about 15 years ago, I think. So yes, as we said, I'm here to talk about a little bit about climate change, about how the climate has changed already, why it's changed, I think we all know the answer to that, and what it means for all of us now, what's going on right at the moment, and also in the future. And the future will depend essentially on our collective decisions made as a global society about how we respond. And so I'll talk a little bit about that towards the end, perhaps. But first, the graphic on the screen you can see are the warming stripes, which are kind of the simplest way we can talk about this issue. They simply represent the change in global temperatures since 1850 up till the present day, 1 year per stripe. And the colours of the stripes show the temperature of that particular year as the global average. And then the simplest way we have of communicating the simple fact that our world is warming and has done very rapidly, particularly over the last 50 years or so. And one single glance at this image tells a very powerful story about what we've done to our planet and what we've done to our climate. But this hides an awful lot of, obviously, detail about how our weather and climate operate. So I always like to start these presentations with what our planet looks like from space. If we look down, this is from the EUMETSAT satellites, which monitor the whole planet every day. And this is last September, I think this starts. So this is just a snapshot, really, about what the weather systems on our planet look like. And there is so much fascinating detail in here. You could stare at this for hours, and I think people do. You can find it on YouTube if you want to look at it afterwards. But we start, I think it's hurricane season, typhoon season. So we can see a typhoon currently in the Pacific about to hit China. Mic's not on? Okay. It's on. I thought I turned it on. So I use this one instead, is that better? Ah, right, okay, fine. Let's take this one off then, that's easier. So yeah, it's a lot of fascinating detail about the weather on our planet. You can see, at the moment, lots of typhoons and hurricanes in all of the ocean basins. It's the time of year for hurricanes. But also, if you look in our part of the world, you can see all of the familiar storms that come across the UK and Ireland and Europe. And you can see similar storms tracking across the Southern Ocean as well. So this is how, this is familiar, north-south. We see storms going across the planet in different directions. In the tropics, we see things maybe moving a little bit in the opposite direction, moving westwards rather than eastwards. And there's so much fascinating detail what's going on over the forested areas, across Central Africa and Northern South America, this bubbling up of cloud and convection, as we call it, in the tropical regions. You can see the sun's reflection tracking across Northern Africa in particular, for example, during the day. And you can see those clouds bubbling up at the same time of day every day. And you see the lovely sort of again, similar convection activity over near Australia, above Northern Australia, for example. And obviously where we are, we can see the storm tracks coming across. You see the interaction between the storms and the land, and the mountains in particular. You can often see, as the storms come across the UK, you see cloud bands caused by the interaction between the clouds and the mountains. You can also see that across the Andes in South America, what the mountains do there to the weather. So it's absolutely fascinating to watch our planet in action. If you see this, you probably appreciate why we live in such a variable climate, variable weather where we live, with gaps between the storms and lots of cloud and rain hitting these islands. So I think that's why the British love talking about the weather, because it is so variable because of where we live in the world and why we've measured it for so long. So you've probably noticed it's been quite wet over the last several months. And in fact, it's been the wettest 18 months on record for England. And our records go back to 1836. So hundreds of people across the country have been recording the rain since about 1836. We have very detailed records across the whole country for that period. And here is what the rainfall in southwest England looks like since that time up to the present day. So one bar is 1 year, one winter. So this is just for the winter time. On average, we'd normally get about 350 millimeters of rain in a winter in this part of the world. But that's gone up by about 30% over that time period, over the last century or so. The winters have got a lot wetter. And that's probably very noticeable, and we've noticed this winter being pretty wet. The winter itself hasn't been the wettest on record. There have been much wetter winters, but not that long ago. You probably remember those. But again, it was a very wet winter, and with the summer and the winter before that, it has been extremely wet, as we've all recognised, I'm sure. So yes, our climate is changing, and the weather is changing. And, for example, we can see it here in how our rainfall is changing in this part of the world. We are a wetter part of the world than we used to be. And that, of course, has implications for flooding across the low-lying areas of southwest England and everywhere else around the country, because this trend is seen across the whole country, not just in southwest England. But what about the summertime? The summertime's a bit different. The summertime hasn't changed very much, the amount of rain we get in this part of the world. It has, in fact, declined very slightly, but not by very much at all. We actually see a very stable rainfall in the summertime so far. Lots of wet years, lots of dry years. We're used to having wet summers and dry summers. That's just how our weather behaves. There is a slight tendency to have a drier summers, particularly in the south of England, but it's a much smaller trend than in the wintertime. So that's what happens. That's what's happening to our rainfall anyway here. The driest summer on record, for the older members of the audience, will remember, I'm sure, 1976, a very famous hot, dry summer. And that is the driest on record for this part of the world. So I'm going to use 1976 as a bit of an example about learning from our experiences of the weather. So, for those who remember 1976, it was a very hot summer. So here is a map of the UK for July 1976 on the left and July 2023 on the right. And the colours are whether it was warmer or colder than normal. 1976, bright red, very hot, much warmer than normal. Actually, last July was not actually very warm. It's actually relatively cold compared to some recent summers. But that's just a fact that we live in a part of the world where the weather is very variable. We get hot periods and cold periods. And last July happened to be particularly cool over the UK. So, this will lead many people to say, well, climate's not changing. We've had hotter summers in the past, et cetera, et cetera. But it's important to see the bigger picture. So this is how we have experienced the weather in a particular way, but it's important to see the bigger picture. So if we zoom out slightly and look at a bigger picture, so they're the same two maps, except we're now looking at Europe rather than just the UK. And in 1976, you can see, there was a small part of Europe which was very, very hot. But the rest of Europe was freezing cold for that summer. And July last year, yes, although we were a little bit cooler than normal, southern Europe was burning red hot. We remember seeing the wildfires in Portugal, in Spain, in Italy, and in Greece last summer, caused in part by the extremely hot temperatures in that part of the world. So it's always important to look at the bigger picture when we're thinking about how variable our weather and climate is. What you experience in one location is not what the rest of the continent or even the rest of the world experience. So let's zoom out again to the whole planet. So if we now look at the whole planet for those same 2 months, we see July 1976, we were the only part of the planet which was really hot that particular summer, basically. And last July, we were probably one of the only parts of the planet which were actually quite cold. And so looking at the bigger picture is really, really important. And now you can see the pattern of warming that we've experienced. So looking at a couple of months in a couple of places, you don't see that big picture. You only see the big picture by looking out, looking everywhere, and seeing the fact that, yes, our climate has changed over that period, even though we may not have experienced it in quite that way with those 2 particular months. And it's also important to see the bigger picture when we look through time, as well as just looking across the planet in terms of looking across space. So here is our local temperature change here in Exeter. So we have records, in this example, going back to 1850 here in Exeter. And again, this is the bigger picture for how the climate in Exeter has changed. We've already seen the change in our winter rainfall and a little bit in the summer, but here is the annual temperature in Exeter. And back in the 19th century and early 20th century, a typical year was about 9.5 degrees for that annual average here in Exeter. We've just had the 2 hottest years on record for Exeter at the very end on the right, more like 11.5 degrees. So again, looking at the bigger picture, you see how our climate has changed. If you had a thermometer in your back garden for the last couple of hundred years, you would see a change of about 2 degrees, 1.5, 2 degrees, about how our climate has changed. You can see climate change wherever you are in the world. At any particular location, if you look for long enough, that signal is very, very clear. So climate change is happening, it's here, it's now, and it is very clear when we look at long records, both in time, but also looking across space as well. So we look now at a map of where the warming has happened. So we have these long records for Exeter. We've got long records in many different parts of the world, and we piece them together across the land and across the ocean to look at maps of where has warmed up over the last 170 years or so, since we've had widespread records. And you can see lots of interesting patterns in this map of where the climate has changed most. We see the most warming, the darkest reds, up in the Arctic. The Arctic is warming faster than anywhere else on the planet, warmed up by 3 or 4 degrees in some places over that time. The land areas are warming faster than the ocean areas. And that's partly explained by the fact that the oceans have what we call a larger heat capacity. They absorb more heat. And so we don't see so much warming over the oceans, but we see more warming over the land. What else do we see? We see a strange blob in the North Atlantic. That may also stick out. It's the only part of the world which hasn't warmed up. And we think that's probably due to the fact that the ocean circulation, the currents in the ocean have also slowed down slightly because of our warming world. And so less heat is being transported northwards by the currents in the Atlantic Ocean. And so that part of the world has not warmed up because although it would be warming if the currents were the same, but because the currents are slowed down, it hasn't warmed. So there we are. That's how the map of our warming world looks like. But what's been causing this? So I'm sure we all know the answer, that the main culprit is the increase in carbon dioxide and other greenhouse gases in the atmosphere. But I'm also going to just briefly highlight how we know this and how long we've known this, because I think this is important to emphasize. So I'm going to talk about these two characters who are John Tyndall was Irish but worked here in the UK, and Guy Callender was an English steam engineer. So this is kind of a sort of British contribution to our understanding of the climate. So what did they do? So John Tyndall, first of all, so he, in the 1850s, was performing experiments in his laboratory in London to understand what happened to heat when it was passed through various gases. And the reason he was doing this is because a decade or two earlier, it had been realized that we couldn't really explain why the Earth was so warm. What our understanding at the time was that actually the amount of energy we get from the sun is not enough to heat up the planet to be more than a ball of ice. The Earth should be a ball of ice given where it is compared to the sun. And so the scientists didn't understand why the Earth was not a ball of ice. And so they thought there must be something in the atmosphere which was stopping and slowing the heat escaping from the Earth's surface. So the way the climate system works is that we get energy in from the sun as visible light. It hits the surface of the Earth or gets reflected back into space by clouds and ice. But what is absorbed in the Earth heats up the Earth, and then that heat is then re-emitted back out to space as heat or infrared radiation. And that those two numbers balance. The amount comes in must balance the amount going out if the climate is stable. And what Tyndall realized was that the gases in the atmosphere, which were slowing down that heat escaping and allowing the Earth to be actually rather warmer, more like 14 degrees of the global average rather than minus 20, was the gases carbon dioxide and methane and water vapor. So they occur naturally in the atmosphere, and so there's natural levels of greenhouse gases mean that the Earth is livable. It has liquid water at the surface, and we can all live and thrive. And so the greenhouse effect, which is what this effect is actually a good thing. It means our planet is habitable. And what we are doing by adding additional carbon dioxide to the atmosphere is amplifying that natural greenhouse effect, making it stronger and warming the planet still further. And this was the apparatus that Tyndall used in the 1850s to test the absorption of infrared radiation by various gases and work out what gases it was that was doing this in the atmosphere. And the answer was carbon dioxide, methane, and water vapor. And so although he wasn't studying the change of the climate at that time, this is the underpinning evidence for why we know that carbon dioxide is responsible for is essentially the key property of the atmosphere which determines our climate. And then about 70 years later, along comes Guy Callender, and he was the first person to show that the Earth was warming, all the way back in 1938. So he put together the available temperature records that he could find at the time, about 150 sites across the world, and this is the graph that he plotted by hand, doing all the calculations by hand, no computers back then, to estimate what had happened to Earth's temperature, Earth's land temperature over the previous 50 years. And he saw an increase in the planet's land temperatures by about 0.3 degrees. So he was able to detect that change using just pen and paper, essentially. But also, really importantly, there's also a very notable little annotation in the top right-hand corner saying CO2 effect. So not only was he the first person to highlight the fact that the Earth was warming, he was also the first person to put together the available measurements of carbon dioxide in the atmosphere, show that the amount of carbon dioxide had already increased because of our burning of fossil fuels, and work out roughly what that should have done to our climate. And he actually found out that the climate had warmed a bit more than he expected from the increase in carbon dioxide. So here we have it in 1938, 85 years ago, more than 85 years ago, we had a complete understanding of the fact that, yes, the planet was warming and that carbon dioxide was at least partially responsible for it. So we've known this for a very, very long time indeed. Except no one believed him at the time. The stronger evidence came over the coming two or three decades when we understood more about the physics and so on. But this is the first evidence that we have. And what does that picture look like today? So this is our understanding of how the global temperatures have changed, all measurements made by thermometers, going back to 1850. So this graphic shows how much our planet has warmed since the 1850s up to last year. The zero is roughly what we refer to as the pre-industrial climate, before the climate was affected by human activity. And so 2023 was just under 1.5 degrees warmer than that pre-industrial period. It was the warmest year on record last year globally by a substantial margin. We smashed the previous record. And as I say, it was about just under 1.5 degrees above the pre-industrial average. There's lots of very interesting patterns in that time series, which we can maybe talk about. But the dominant influence on that is the increases in carbon dioxide in our atmosphere and other greenhouse gases. And again, here with the stripes are below, showing the same data, just in a very different way, a different visual way. And so, traditionally scientists would use the traditional line graph at the top to communicate this, but the stripes showing exactly the same data are at the bottom, just to highlight that they are a useful tool, one useful way of communicating about how our planet is warming. They highlight that warming very visually, very clearly, but they don't have all of the interesting information that is included in the top graph, which about the size of the change or the uncertainty in our estimates, which is shown by the little grey shaded areas. So there's different ways of showing the same data, and these are just two examples, but both show that our planet has warmed very significantly. But it's also important to zoom out again and see the even bigger picture, as I've been highlighting already. So what we want to try and do is put this recent change into a slightly longer term context of the last 2,000 years. And so when we look back over the last 2,000 years, we see again a very stark picture. So first of all, we focus on the little red line to start with. That's the level of carbon dioxide in the atmosphere over the last 2,023 years. We have records of carbon dioxide mainly from bubbles stored in ice cores. So as ice freezes in Greenland and Antarctica, it stores the air that was in the atmosphere at the time, and then we can dig large ice cores up and sample them and measure the amount of what the atmosphere was doing at the time. And so we have very good understanding of what the levels of greenhouse gases were in the atmosphere for for hundreds of thousands of years, but this is the last 2,000 years. And we see that, before the Industrial Revolution, before the invention of the steam engine, the carbon dioxide levels were pretty flat. So this is the natural level of carbon dioxide in the atmosphere. That's responsible for the natural greenhouse effect. And what we have done since the invention of the steam engine and the Industrial Revolution is rapidly increase the amount of carbon dioxide in the atmosphere, and so enhancing the greenhouse effect and making our planet warmer. And we can see that in the blue line, which shows our reconstructions of global temperature also over that time. And these reconstructions come from things like tree rings and coral records and many other natural archives which store information about the temperature at the time. And that's more uncertain, but what we see of the same period is the fact that, again, the climate was fairly stable for most of the last 2,000 years until the invention of the steam engine and the Industrial Revolution, and we see the rapid increase in temperature since that time. And more importantly, we understand the physics of why this happens. We understand the physics of how the planet, why carbon dioxide would cause a change in temperature, about why it absorbs infrared radiation and therefore warms the planet. And so we understand the physics, and everything is consistent. It's a consistent picture of our understanding of what's happened to our climate. And this change is unprecedented in that period, as we can very clearly see. So what else has happened to our climate since we've had pretty good observations? So we have satellites measuring the planet since about the late 1970s, and they essentially take photographs and measure all kinds of fascinating things about the weather and our climate. And they have watched over that time as the Arctic ice has melted away, particularly during the summertime. We've lost about a third of our summer sea ice over the Arctic since the 1980s. So in the 1980s, the ice was typically covering the white region. In 2023, it was covering the blue area. And so, yeah, we've seen the shrinking of the Arctic sea ice, particularly in the summer months. And that's important because the ice in the Arctic reflects a lot of sunlight back to space. So if you take away that ice, the Earth absorbs more of the incoming heat from the sun, and so amplifies the warming. And that's why one of the reasons why the Arctic is warming faster than anywhere else. It's because we're taking away this reflective layer of ice and exposing the dark ocean below. So that amplifies the warming that is coming from the fact that we're just living in a warmer world. And in this sort of same part of the world, we also monitor what's going on, for example, on Greenland. We actually measure the mass of Greenland from space with a mission measuring the gravity, how much gravity Greenland produces. And Greenland is currently melting at a rate of 4 litres of water per person on the planet per hour. So effectively, every hour, every person on the planet is pouring 4 litres of water into the ocean, just from the melting of Greenland. And equivalently, that's 3 Olympic-sized swimming pools of water every single second, going from Greenland into the ocean. That's a lot of water. So what does that do to the ocean? So the ocean obviously now has more water in it. And also the ocean is warming, as we've seen previously. And so what happens as water warms up, it also expands. And so what is happening in the ocean is that the water is warmer, it's expanding, it's taking up more volume, so it's rising. And then we're also adding more water to it, so it makes it rise even further. And so what we see when we look at our records of sea level is that sea level is increasing. And so this animation hopefully shows, here we go, our records of sea level since 1900. And you can see sea level slightly creeping up pretty slowly at first, 5 centimetres in the first 40 years or so. And over time, we can watch as the sea level increases, again, fairly slowly. But then, over the last decade or two, we see quite a sharp acceleration in the rate of sea level rise. So we've now had nearly 25 centimetres of sea level rise so far over the last century or so, and that rate of increase is speeding up. So we're seeing more rapid increase in sea level more recently. And that's equally due to the fact that we are adding more water to the ocean from melting Greenland and the glaciers and Antarctica, and the fact that the water is warming and becoming more volume is coming in the oceans because it's warmer. And so what does that mean for us? Well, around our coastlines, they're having to deal with 25 centimetres more water on average at height around our coastlines. And for sea level in particular is one of the consequences of climate change, which is going to persist for a very long time. Because that extra heat in the ocean is going to gradually go deeper and deeper in the ocean, it's going to warm up more and more of the ocean, the water is going to keep expanding, and so sea level is going to continue to rise for centuries. And we can change the rate at which it happens by slowing down the rate of global warming, but we're not going to stop sea level rise. It's going to keep going. And Greenland and Antarctica will also keep melting even if we stabilize global temperatures. So we're going to keep adding water to the ocean, and the seawater is going to continue to expand. And so we are locking ourselves in for a metre or maybe several metres of sea level rise in the future. And so we have to think about what we're going to do to our coastal cities, or London, with 1 metre or 2 of sea level rise. How are we going to adapt to that? What are we going to do to London to deal with 2 metres, for example, of sea level rise? It will take centuries to happen, but we are going to have to deal with it at some point. And so what other sort of types of effect are we looking at as a consequence of our warming world? So maybe start in the bottom right. We've got a picture, this is from Bangladesh, very low-lying area. And of course, sea level rise in Bangladesh is causing very severe problems for the people in that region, which are flooding very much more often than they would otherwise have done because of rising sea levels and flooding farmland and so on. And so they're facing very severe consequences from rising sea levels and will not be able to live there in those regions. And so, that will force migration from low-lying areas in Bangladesh and other countries as well. Maybe staying in the ocean in the top right, we're starting to see corals bleach around the world. And so here is a picture before and after a particularly intense warm event in a particular location. And what happens is when corals get too hot, they bleach and turn white. And if the water doesn't cool down fast enough, they will die. And we're seeing mass die-off of coral reef in many different parts of the world. And coral reefs are our nurseries for ocean life. And if we mess with them, we're going to mess with the whole ocean food chain. And the consequences of that, I think are rather uncertain, but they're not going to be good for our ocean ecosystems. And many people, millions or billions of people around the world rely on seafood as their main source of protein. And so if the fish move or can't survive, then that's going to cause big problems for how people survive in those regions. In the bottom left, we see a rather major, impressive wildfire. I'm sure we saw similar examples on the news last year, from places like Rhodes and Portugal and Spain. I think this one's actually Australia. And so what's happening is as the climate is warming, we're getting hotter heat waves. So every heat wave is now hotter than it would otherwise have been because of climate change. And not only are they hotter, so the hotter weather also dries out the soils. It causes more evaporation from the soils, meaning there's less moisture in the soils. And that means it's drier, which means it's more conducive to wildfires. And so when wildfires start, they become more intense and more widespread. We actually saw in the UK in 2022, when we had the 40-degree heat wave here in the UK, there was actually one wildfire on the edge of London which burnt down several houses. It's pretty unusual, I think, to get a wildfire like that here, but it may well become more frequent in future, especially around the edges of towns and cities where we're exposed to areas which can catch fire more easily. And in the top left, we see a flood. I think this is from the Somerset levels. And I think this is one of the biggest risks that we face in the UK in particular. As we've seen, our winters are getting wetter. And every storm that we have brings more rain than it would otherwise have done. And so our river systems are going to struggle to deal with that much more water. Especially, we're also altering what we're doing in our towns and cities about where water goes when it reaches the surface. And that's not helping either. But we are seeing more rain falling from the sky, which we're going to have to learn to deal with somehow. We're going to need to learn to adapt or just deal with the consequences of increased frequency of flooding or the risk of flooding in many parts of the country. A couple more examples, perhaps. So the picture on the left is probably a familiar one. This is the Dawlish railway line when it got washed away a few years ago. And here, this is another example of how climate change makes what was an extreme weather event, makes it worse, or makes the consequences of that extreme weather event worse. Yes, it was a very unusual storm that caused that storm surge around Dawlish and washed away large parts of the railway. But because the sea level was higher, 25 centimetres or so higher, that means there was a bigger storm surge. The waves reached further inland and were higher up, which therefore caused more damage. Not to say some damage wouldn't have happened, but the damage was worse because the event was made worse by the fact that sea levels were higher. So this is an example of how climate change is not causing the events to happen itself, but it's making the effects and the consequences worse than they would otherwise have been. In the bottom right, we see a glacier, and this is there to highlight that, yes, our glaciers are melting, This example is from Switzerland, I think. We see a sign there in 1995 saying where the end of the glacier was. That's where the end was, and now we can see it far back in the distance. And the reason this is important for many regions is that, for example, in the Himalayas, for example, and the cities downstream of the Himalayas, they rely on meltwater from glaciers as their source of fresh water. And so if the glaciers are gone or melting, then their supply of fresh water is going to dwindle away as well. And so that is another very important impact for certain parts of the world. So I'm trying to highlight, I think, that there are different risks depending on where you live in the world. If you live around your coastline, you're perhaps more worried about sea level rise. If you live in other places, you're facing different risks depending on where you are in the world. And the top right photo shows a drought. This is from the Amazon last year. The Amazon is extremely dry at the moment. And again, when we get low amounts of rain, then we're seeing droughts. But those droughts are made worse because the weather is warmer, causing more evaporation from our soils. And if you're farming in many regions where you're relying on the moisture in the soil to grow your crops, although you may get slightly less rain, but you're getting a much bigger change in your amount of water available for the crops to be able to grow them. And we're seeing that in other parts of the world as well. So climate change affects all of these different things in many, many different ways. I'll move on. I'll not say that. I'll move on. So these are just some examples of the risks that we face in different parts of the world. We see all kinds of risks listed here, and I've talked about some of them already. We're seeing more intense floods because the atmosphere is holding more water, because it's warmer, it's more humid. So when we get storms, we get more rain falling from the storms, which is mainly why our winter rainfall is increasing. And so that means that when we get more rain falling, we need to learn how to deal with that water because it's going to increase the risk of flooding. Heat waves we've seen, when the UK hit 40 degrees a couple of summers ago, we saw major problems for our infrastructure. Our roads, our railways, our electronics that live outside, we're not adapted to experience those temperatures. And so infrastructure struggles when it's exposed to temperatures it's not designed for. And we're pushing our climate, so we're experiencing those very hot temperatures more often and cold temperatures less often. And so that means we might need to redesign our infrastructure to deal with an average hotter climate. Not to say we can't do that. Many other countries live with hotter conditions than we do here, but it's expensive. It means we need to rebuild things and redesign things to deal with the change of climate. What else have we got on the list? There's lots on the list, as I'm sure you can see. Disease movements. We've seen a massive increase in dengue fever in the tropical regions over the last decade or so because there's better conditions for mosquitoes to thrive in those regions. And so we're seeing massive spread of tropical diseases moving northwards and southwards out of the tropics into other countries which would not normally experience such diseases. And maybe southern Europe will start getting affected from some of these diseases fairly soon. And that may affect what happens when you go on holiday to some of these countries as well. You may well be exposed to diseases that we would not normally expect to see. If you live around the coastline in the US or in Asia, which experience typhoons and hurricanes, what we're seeing is an increase in intensity of hurricanes because when hurricanes pass over the ocean water, the ocean is warmer, it provides more energy to the hurricanes, they become more intense than they would otherwise have been. And so, again, coupled with the rising sea level around the coastlines, it means that hurricanes can cause more damage. We're seeing changes in the jet stream, for example. We're seeing glacier loss, coastal erosion. Even if you're flying, now we're seeing actually an increase in turbulence in the atmosphere because the atmosphere is warmer. And so pilots and airlines are reporting an increase in turbulence, and that's what we see in our data as well. And we're going to have to deal with infrastructure failures as infrastructure is exposed to a climate that it doesn't normally see. So what's happened globally because of all these risks? The science has told the world's governments these are the risks that we face, and this is why we're facing those risks. And so in 2015, the world came together at Paris and signed the 2015 Paris Agreement, which aims to stop global temperatures increasing. Note that it is not there to cool temperatures down. We're not trying to do that. In fact, that's going to be almost impossible. All we're trying to do is stop the situation getting worse. And so to stop global temperatures increasing, we need to get to global net zero emissions of carbon dioxide. That's the only way we stop the planet heating up. And so that's the global aim that we have to achieve if we are to stop the situation becoming worse. So what does net zero look like? So it's a term we often hear. And what it means is that we have to reach a situation where we have reduced our emissions, our human emissions of greenhouse gases like carbon dioxide. But some of that will be very, very difficult, if not impossible, to stop, actually, particularly in agriculture. And so we also need to find ways of sucking CO2 out of the atmosphere to counteract the things that we can't stop doing or are very, very hard to mitigate. And so we need to make rapid changes if we are to stabilise global temperatures at the levels which the global governments have said they would like to stabilise them at. And so this is kind of a pathway that we would have to follow if we are to meet the Paris ambitions to stabilise global temperatures at pretty at reasonable levels, the levels which were specified in that agreement. That looks pretty challenging. You know, that's going down more than twice as fast as we've gone up in our emissions. And our emissions are dominated by fossil fuel, burning fossil fuels, so burning coal, oil, gas, petrol, diesel, and everything else. And there's a chunk there due to the fact that we are changing our land use, mainly deforestation, not only, but mainly. And so because we're still chopping down the world's forests, that is releasing carbon dioxide to the atmosphere as well. But the giant chunk is due to burning fossil fuels. And this bit under that dashed line is called our carbon budget. It's the carbon we are allowed to spend if we are to keep to the ambitions of the Paris Agreement. So there's some very fascinating questions there about how we split up our remaining carbon budget. Who gets to burn the carbon if we are to meet these targets? And that's, you know, a very complicated geopolitical question. I'm not going to suggest an answer because that's for the geopolitical experts to decide. But there's a whole range of very complicated moral, ethical, historical issues there about how we are allowed to spend our carbon budget globally if we are to meet those aims. So, again, science doesn't tell us exactly how to reduce our emissions or when to, but what science can tell us is that the faster we do this, the less bad the consequences will be. Every ton of carbon dioxide we add to the atmosphere will make the situation worse, adds to the warming. And so every ton of carbon dioxide emissions that we avoid reduces those risks and means they don't get even worse. And so if we're interested in the climate consequences, then the best outcome is to reduce emissions as fast as we can. But there are other complicating factors, of course, about what we do with our engineering and our economy and poverty and all of the other complicated issues which come into the equation about how we achieve this fairly across the globe. So in the UK, our part of that puzzle is that our target, legally binding target, agreed by all the political parties, is that we are to reach net zero emissions by 2050. That's our target that the politicians have set in the UK. So how are we getting on? I don't have a very pretty picture for this, unfortunately, but so the latest data actually came out very recently. So these are emissions in the UK by different sectors. So, for example, the black line shows what's happened to our emissions due to energy generation, electricity generation mainly. And that black line is the positive story we have to tell in the UK, right? We have done very well, particularly over the last decade, in reducing our emissions from energy generation. That's mainly because we've switched off our coal-fired power stations. It's almost entirely due to that, in fact. We used to burn a lot of coal, even back a decade or so ago, but we've reduced that, and so we've reduced our emissions by switching to gas and renewables quite substantially. But that's the really, really, really easy bit. Everything else is much harder. So we have done the easy bit very well. Now comes the hard bit. And so now the biggest chunk of our emissions in the UK comes from transport. So that's, our cars, our vans, our lorries, buses, trains. So we've made a little bit of progress there, but not a huge amount of reducing our emissions from transport. And of course, there is obviously a big push for electric vehicles, which will help that situation. What else have we got? We've got buildings. Again, we've made some progress about energy efficiency in buildings, but again, not as much progress as we might, and we've got a long way to go if we are to get all of these lines down to close to zero, right? That's what we have to try and achieve by 2050. And that looks pretty challenging, especially as sort of agriculture, the flat line, we've not made any progress at all. And some of that will be actually very hard to stop emitting, because we need to grow food, right? We can't stop growing food, but we can make reductions in agriculture as well. And what's the last line? Industry. And of course, we've offshored a lot of our industry, and so we've reduced our industry emissions, and in some industry have become more efficient as well. So we've reduced our industry emissions as well. But if we are to meet our self-imposed carbon budgets, so these are the government-agreed targets that they would like to achieve. We need to halve our UK emissions over the next 11 years. So by 2035, we need to have halved the values, so the lines need to move halfway towards zero, and by 2050, we need to be at zero, or close to zero, because we might have then invented a way of sucking the CO2 out of the atmosphere efficiently and storing it underground somewhere. But that might offset a small amount of this, but it definitely can't do the whole job. So we have to reduce our emissions rather drastically if we are to achieve the aims that we've set ourselves. So there's lots of difficult choices. Some are simple, some are very complicated. We have to decide about how we reduce our emissions fairly across the globe as well as here in the UK. Who gets to decide where we make the quickest and the biggest cuts? There's always going to be trade-offs about how we achieve this. What do we do with our land? We want to grow more trees, but we also need food to grow food as well to live. So what do we do with our land to achieve these aims? What do we do about the economy or energy security as well as our energy generation? These are very complex decisions. So the climate becomes one part of the equation into making these decisions, but it's certainly not the only aspect of how we choose to move forward. We're going to certainly have to be more efficient about how we use our energy, especially in homes, I think, our heating, for example. We're going to ask people probably to change their diets a bit. And we are going to have to think about how we deal with poverty around the world, how we transport ourselves around. And we're also going to need to decide how to spend money on adapting to the changes we're already seeing. We're already feeling the consequences. We are not always dealing with those consequences very well. People are suffering because of the worsening extreme weather, so we need to adapt and deal with those situations better. So how do we spend money between reducing our emissions on one hand and adapting on the other hand? And some of the choices are easy because actually they save us money. Right? Currently, if we generate electricity from wind, it's much cheaper than getting it from gas. So some things will save us money, some things will cost us money. And so we have choices, and I think that's the kind of the point that I would like to highlight really, again, is that it is our choice. Because we are causing the problem, we get to choose whether to stop it or not. So it is on our hands to decide what happens next. We can take very rapid action and reach net zero by the 2050s as a world, and that will stop the planet heating up. It won't reverse the situation. It will just stop the situation getting worse. Or if we delay our action or don't bother, we're going to end up in a much, much warmer world, 3 degrees, 4 degrees. I don't think that's the type of climate we want to live in, actually. And so it's down to our global choices about what we do. And the consequences of the decisions we make over the next decade or so are going to live with the planet for generations. We are living through the time where the decisions we make will affect the climate for generations, for our kids, our grandkids, and the generations beyond as well, particularly with sea level rise and temperatures and extreme weather. We are committing our future generations to the climate that we decide on over the next decade or so. That's a big decision. So, it is unequivocal that human activities are warming the climate. That's the word that the Intergovernmental Panel on Climate Change chose to use. It means scientifically certain. right? That we are warming the climate mainly through the burning of fossil fuels. We're already experiencing the consequences. We're already seeing extreme weather events becoming worse, and the consequences becoming worse because we are living in a warmer world. We're seeing more rain from heavy storms. We're seeing hotter heat waves and bigger storm surges because of the sea level rise around our coasts. So we're already experiencing the consequences, and the risks only increase with every bit of further warming. So every action we take makes a difference by reducing our emissions and therefore reducing the amount of further warming. I think the worst impacts that we'll experience will often be, not only, but often be through more intense and more frequent extreme weather events. That's when we often experience the weather the most. We won't necessarily notice a 1 degree temperature rise on a day, which is not very extreme. We probably won't notice that very much. Our plants probably notice it with our flowering earlier and so on, but we probably won't. But we will certainly experience that 1 or 2 degrees if we get a big heat wave and our infrastructure is pushed beyond the limits to which it's designed. So the choices we make over the next decade or 2 or 3 will determine the climate for generations. And the faster we act, the less severe those climate consequences will be. Many of the solutions to achieve net zero already exist and already available. And that if we enact all of those solutions and invent new ones en route, then we can achieve net zero emissions and therefore stabilise our climate and stop the situation getting worse. So I think that's the hopeful message I want to leave you with. It can be pretty bleak, right? But we do have hope because we're in charge. We get to decide what happens next. We are causing the problem. We can choose to act and stop it getting worse. Thank you.
And so when I was at university, some of these things were known about, but obviously we know so much more now, and it's utterly fascinating to hear someone who's absolutely at the heart of it talk about his work. So thank you so much, Ed. We do now have time for some questions. So if you have a question, I've got one, but I'm not allowed to ask it unless anyone else doesn't come up with it. Has anyone got a question? Yes, we've got some at the back. Zoe, could you? Yeah, lovely, thank you. Okay, wonderful.
Okay. Is this working?
Yes.
Yes.
This is good. Okay. Please, would you like to tell us some of these solutions, please?
Sure. First of all, the solutions are not my area of expertise, right? I'm a climate scientist. I'm here to talk about the risks. But some of those solutions obviously include switching our transport to be electric rather than fossil fuel-based, here in the UK, for example. We are phasing out petrol and diesel engines, and you'll not be able to buy the new ones soon, after about another decade or so. So we are moving to electric vehicles. We need to ensure the infrastructure is there to make that happen. So that's one part of the solution. We also need more renewable sources of energy. And the National Grid have come out and with the plan to achieve this, that we can build enormous offshore wind turbines in the North Sea and overproduce electricity most of the time, so that we can supply enough electricity to the country to power our needs if we build a lot of offshore wind turbines, for example. So other solutions, we also probably need to change our diet. We probably need to move, not entirely, I wouldn't say away from meat, particularly beef and lamb. They are the two worst offenders for emissions from the food that we eat. And so the plans that the government have for our pathways to reaching net zero do include a reduction in the amount of meat that we eat as a nation, particularly beef and lamb. Heating at home, we are also going to move to electric heating at home through heat pumps. There are complications in some houses trying to fit those, but we're still building houses which need gas, right? Which doesn't seem to make much sense to me. But anyway, we have many of the solutions to achieve a lot of the reductions. Some we're going to have to invent en route as we go, but many of them are available and in some cases will be cheaper.
Okay, thank you very much.
And
So we can all rush out and do all of those things now.
Can I add one other thing,
Yes.
particularly about the transport aspect, is that we would want to switch to EVs anyway because it improves our air. The petrol and diesel that we burn makes our air quality really bad and causes so many health problems, asthma, as well as many other conditions, which are a huge drain on our NHS. And so by switching to EVs for climate reasons, we also massively improve our air and will improve the nation's health as well.
There we go. Are you going to go and run out and do all of those things?
No.
Another
Actually,
question, thank you.
There's one little thing that comes from that, Ed. And first of all, thank you very much for a fascinating talk. We're going to try and do all of these things. I'm sure we will, and a lot of us are trying to do things now. But we're tiny. And China is rather large, so is India, so are the States. How are we going to put a lot of pressure on them to deal with it? That wasn't my original question, actually. Okay. If I get a chance, I'll ask you that a bit later.
Fine. Look, this is a global problem, right? You know, every country has to reduce their emissions. How we do that fairly and when each individual nation should do that, I think that's a very thorny issue, which I'm certainly not going to go near. But, you know, for example, China is building more solar and wind than the rest of the world combined at the moment. They are soaring ahead. They're developing the technology to build massive solar and wind farms, and as I said, more than the rest of the world combined. They are surging ahead, and we're getting stuck behind. We could be inventing the technology to be able to do this and be selling it ourselves. But so no, many countries are forging ahead, even though we don't necessarily always hear about it.
Okay, thank you. Another question? Yes, at the front here.
You've talked a lot about fossil fuels, your area of expertise, and what you haven't mentioned is the impact of other dreadful things going on in the environment, like plastic. And one of the risks about plastic is the risk on fertility. So what is going to be the impact of decreased fertility and change in demographics and the worldwide population on the impact on climate change of fossil fuel use and building infrastructure and so on?
Well, I think, you know, largely speaking, we are going to, by moving to renewable energy sources, we are going to decouple a lot more to decouple the link between population and emissions. We're already unlinking GDP and emissions, but we will also eventually make that link far weaker than it is at the moment by moving to a renewable energy source. So because we just won't be producing the emissions. And so the population, you know, although consumption and everything, you know, have important issues as well, but from a climate perspective, we will decouple that link.
Okay, thank you very much. Another question? Yes, our chairman.
Ed, thank you very much. Very interesting. And of course, we're all into solutions now because you've scared us to death. Two questions. One is energy storage. How do we go about that? Mm-hmm. The other is how do we remove the carbon? You mentioned that agriculture is going to be the challenge.
Yeah. So yeah, I mean, well, so if we are to live in a say country, or you know, here in the UK, if we're going to generate a lot of energy from wind, offshore wind in particular, we can bring that onto the land and use it. And most of the time, we will have far more wind power than we need if we build the amount that we're planning on building. And that means we can store that energy. We can store it, for example, in batteries or probably in hydrogen, I think is the big opportunity. We can use excess electricity to electrolyze water to make hydrogen, store the hydrogen, and then we're able to burn that when we need it as a backup. So that is one of the options that we have available to us. The House of Lords produced a very interesting report last week on energy storage. So, you know, you can go away and read that about, you know, all of the options available and what we need to do to achieve there's several different options for energy storage, which we can implement to have available to us when we need it. You know, we are going to have to, you know, we'll be able to export electricity as well when we have too much. as well as recharge our batteries, if you like, as well as other sources to provide us with energy when we need it.
So capturing carbon and putting that...
Yes. So, so there's different aspects to this. So, obviously, the most obvious way we can capture carbon and lock it up is by planting trees. But you can only do that once, right? You can plant a tree, it grows, it locks up a certain amount of carbon, and then if it dies, you then have to replace it, right? And so when it dies, it releases all that carbon back up to the atmosphere that you've very carefully stored, and so you have to wait for the tree to grow again. So that will probably be part of the solution, right? But it only counts once, right? You plant a tree in one place, it stores the carbon, the tree dies at some point, and you regrow it, but that regrowing doesn't count again because it's recycling, if you like. So that's one way we can have a one-off benefit by planting lots of trees and waiting for them to grow. They take a long time to grow. Other ways, there is one, I believe, commercial plant in Iceland which uses geothermal energy to power a chemical process which absorbs CO2, and then they pump it underground. And the geology in Iceland, their site, is that such that it stays underground, reacting with the rock in that particular location, and is locked up in rock form underneath the surface. And so, there are some very baby technologies available, but they are, it's a minuscule amount at the moment, and it doesn't work everywhere. You need a certain type of geology to make that process work. And there are other small baby steps being made in other ways of sucking CO2 out the atmosphere. There's even talk about trying to take it out of the ocean, because there's a lot of there's actually a lot of carbon absorbed by the ocean. So in fact, the ocean is becoming more acidic because the ocean is taking up a lot more CO2. And so if we take out the CO2 from the ocean and bury it underground, that would also work. And so there are ways, people are thinking about ways of trying to do this. We need to work harder, I think, to invent that technology and make it more efficient. But there are steps being made.
Okay, thank you very much. Any other questions? Yes.
The risks you describe so well require radical and timely action. Are you concerned carbon capture and storage could be a distraction that stops us from doing all those things?
Yeah, so it's a carbon capture and storage. So that refers essentially to we could retrofit or build new power stations that use fossil fuels, but as we are burning those fossil fuels, we capture this carbon dioxide at the source, don't let it go into the atmosphere, and then bury it underground somewhere. Again, I don't think there's a major plant that is doing this operationally. Again, there's lots of ideas about how it could be done, and certainly some developments in that direction. But again, it doesn't work everywhere because you need a place to store the carbon dioxide once you've captured it and liquefied it. So yes, it could go underground in certain places, but it doesn't work everywhere. And if the carbon dioxide escapes from where it is, it just goes back into the atmosphere and warms the planet again. So I do think it's a bit of a distraction. We may need some of it, I think, because we are, well, if we're not acting fast enough on reducing our emissions, then we may well need some of it to sort of slow down the emissions, if you like, and that may well be one option available to us. But I don't think we want to rely on it as a long-term solution.
Okay, thank you. We've got time for one more question. Yes, at the end here.
What I was going to say was that I wanted to, the solutions are not that straightforward. Obviously, EV vehicles are the way forward. However, the other side of that is the recycling of the batteries, which can cause another problem. So is there any comment that you can pass on that?
Yeah, I mean, again, many companies are working on recycling batteries, and we need to definitely work harder at capturing the rare earth minerals that we need from the things that we make and throw away. We throw away an awful lot of very valuable material which we could recycle and reuse. And the same goes for batteries as well. So no, there's definitely opportunities there for, again, new technology to improve the situation, I think.
Okay, now I did have a question and none of you has asked it, so I'm going to ask questions. And that's, Ed, how did you come up with the stripes?
I'll put some examples up. Well, so back in 2018, I was invited to speak at the Hay Literary Festival. So many of you will know the little town village of Hay on the English-Welsh border has a very famous literary festival every year. And normally they, invite lots of famous authors to turn up, and people pay to go and see them. This year, or that year, they had decided to do a partnership between some authors and some scientists, environmental scientists. And so they put on 3 events, of which I was invited to do one of. And I was partnered with an amazing poet and children's author called Nicola Davies. And so she wrote some very beautiful poems about climate and so on. And I was there to talk about the science of climate to that literary audience. And I wanted a way of talking about the issue which didn't use numbers and axes and graphs because of the audience I was going to be speaking to. They were not there for a science talk, they were there for a literary festival, and so I wanted as simple way as possible to communicate. And so that was where the sort of the motivation came from. And I remembered that I had a colleague at the university, the previous year had knitted a blanket for a colleague who was having a baby. In fact, that colleague now lives here in Exeter. So this blanket is in Exeter now. So my colleague had chosen to knit this blanket with stripes, with very colourful, with a leftover wool, very colourful, but had chosen the colours of the stripes depending on the global temperature in a particular year, or a set of years, in fact. And so that was a big inspiration for then designing the graphics in a way, with I think the choice of colours to try and communicate hot to cold in a far more intuitive way. But that was, there was this inspiration from knitting, this motivation of going to the literary festival, and the desire that we need a simple way of communicating that, all came together, I think, to produce it. And what's been so brilliant is that other people have taken the idea and run with it. And so there's some examples up here, which some of you will be familiar with, I'm sure, but there was a rock band in the middle right called Enter Shikari who decided to put them as a backdrop at Reading Festival main stage and use them through many of their gigs as well and talk about the issue live on stage. So again, it starts conversations amongst a very different audience from the people who would normally talk about climate change. And in the top right, we have London Fashion Week. An amazing fashion designer called Lucy Tamam did a range of outfits inspired by the stripes at London Fashion Week. It's not normally a place that climate scientists end up, but there I was at a catwalk show. And then the bottom right is an example from Germany. A group in Germany decided to paint stripes very large on a bridge in Leipzig. That's one of the biggest examples we've seen, permanent examples. Reading Football Club and also put them on their kit last season. So on their home kit, which you can see there, and also on their away kit, which was pink bands, also with the stripe colours, stripe represented as well. Greta used it on the front cover of her book. And then last year we started an effort to try and create a bit of a light up landmarks with the stripes. And so that example is from the White Cliffs of Dover last June, so we projected the stripes very giant size onto the White Cliffs of Dover. And we also did the Tate Modern as well last year, so the Tate Modern chimney we also projected onto. And we are certainly in the planning stages of finding new landmarks for this year, and I hope there's going to be some exciting landmarks that you might see used this year.
So now we know it's all about a jumper, a blanket, a knitted
yes.
blanket, and very impressive. So thank you so much. We do have 2 of our pupils, Georgia and Nick, who are going to give the vote of thanks. So over to them.
Thank you, Professor Hawkins, for a really interesting talk on our changing climate. For me, I found it fascinating how you have managed to use a simple graphic design to convey something so important but also complicated so that everyone can understand the impact climate change will have.
For me, I found the effects of global warming on the ocean to be the most interesting and also worrying. And I hope that the warming stripes will continue to bring about positive publicity for such an important global issue.
The work that you do, spreading awareness for climate change in such an accessible way, is amazing. As students at the school, it is so important and inspiring to see the work that old Exonians are doing. It encourages us and shows us what can be achieved.
So once again, thank you so much for your insightful talk, and we hope you'll accept this gift as a token of our appreciation.
That's very kind. Thank you very much. Thank you. Thank you. Thank you. Thank you. That's very kind. Thank you.
And it leaves me just to thank everyone, to thank Ed again. It's been an absolutely fascinating evening. Thank you so much. We do have the sound of chinking glasses at the back. So please do go and avail yourself of some refreshments. Thank you very much. So